is the celebration of India at 75 and also the celebration of 80 years of CSIR. Today's webinar is on desalination technology used for removing dissolved salts from the saline water. CSIR Research Laboratory, Central Salt and Marine Chemicals Research Institute, CSIR CSMCRI, Bhavnagar is one of its kind, known for its excellence in research of salts and marine chemicals, and has initiated the research program on membrane-based desalination of water. The laboratory has come up with the membrane desalination technology, the topic of the talk today. We are connected with experts to know about the technology, and among the experts, we have Director CSIR CSMCRI Dr. Kanan Srinivasan, Mr. Vikram Karunakaram, Uniflux Membranes LLP, Dr. Tina Chakravarti, R&D Tata Steel Limited, Jamshedpur, Ms. Bhumi Raval, Deputy Executive Engineer, Gujarat Water Supply and Sewage Board, and Dr. Poyam Singh, Senior Principal Scientist, CSIR CSMCRI. So I welcome you all once again. I am Dr. Shikha with you, scientist from Science Communication and Dissemination Directorate. So we shall begin our talks with an opening remarks by Dr. Kanan Srinivasan, Director CSMCRI, who is himself an expert in chemical sciences and holds a specialization in the field of heterogeneous catalysis and material chemistry. So I request Dr. Kanan Srinivasan to kindly deliver the opening remarks for the session. Over to you, sir.
Thank you, Shikha. Good afternoon to everyone who is participating in this webinar. And I'm sure that all of you are aware. In case for a kind of a brief introduction, CSIR has been celebrating 80 years of its existence, and 80 success stories are going to be showcased in this program, which Dr. Shikha has been coordinating and organizing it. And the institute which I belong, CSIR Central Salt and Marine Chemical Research Institute, is a only laboratory in the state of Gujarat, and it has been working on the field of different domains like salt and marine chemicals, marine microalgae, marine macroalgae, and also, we have been pioneering in the field of membrane-based desalination. The reason being, all our activities are centered around the sea. That's the whole idea under which the institute has been traveling its research direction over the last 7 decades. What is more important on this today's webinar is I'm accompanied by several of the distinguished speakers and the users and the collaborators who have been going to share the learnings what they have got in the whole journey of membrane-based desalination. To give a kind of to set the kind of a platform, I just wanted to say why desalination is important, because I think one of the things is very clear that the coastal pockets of the country, the salinity and the groundwater salinity is on the constant rise. Okay, and there are places where you don't have any other alternative source other than the brackish water and seawater. So how do we basically make a potable water for the either for the domestic use or for the industry use? The only alternative is desalination, and of the desalination, largely 90% of the desalination processes are commonly done either through a process called as a reverse osmosis, which my colleague will anyway talk about it, or a kind of a membrane flash distillation kind of a technology, which is a thermal distillation technology. So these are the two major technologies which encompass the desalination methodologies. Of this, the reverse osmosis based, the process which is involving the reverse osmosis, which is operated through membranes, is a technology which is considered as one of the most cost-effective technologies among the technologies that are involved in desalination. So why, having set the tone, why we have to basically look for this one As I said in the beginning, I mean, we have told about the requirement of the water in the coastal places. If one were to see country like India, okay, I mean, we have been continuously been what do you call using our groundwater system so extensively. Our per capita availability of the water since our independence has fallen by something like around 4 times. Okay, at some point of time, at the time of independence, we are considered as a kind of a water surplus country, and now we are going into a kind of a water starved, or I mean, kind of a water resource depleted, a depleting kind of a scenario country that we are basically entering into. And this is not a good news. This is not a good news. We need to have different ways by which we need to have the water regeneration methods, recharging methods, and then treatment methods. And of these methods, the treatment methods is what we have been associated with. And having said about this, there's a lot of work has been done on desalination. In India also, there has been a kind of a greater interest on the desalination. There are plans have come up, a few large size plants have come up, both for the domestic as well as industry use. The good news that I am seeing it is the necessity of desalination projects has been, what do you call it, really noticed very clearly for the states like Tamil Nadu, Gujarat, Andhra Pradesh, Maharashtra, where I mean a lot of many desalination projects are coming, and the total kind of an investment that desalination projects are likely to give is at least in few $1 billion in the next few years to come. What is all the more important? I don't want to talk about what the institute has done. Anyway, my colleague Dr. Priyam Singh will cover. What is all the more important is, it is not about the desalination per se, especially the membrane-based desalination per se, should be adopted in a kind of a way which is sustainable and which is not posing any kind of what do you call a difficulty for the ecology or the environment. And that is where, I mean, we need to have a kind of a greater what do you call a responsibility while we are doing the membrane-based desalination. And there have been a lot of efforts done by this institute in terms of different ways by which one can handle the reject brine management. And this is one of the most important what do you call parameter that one has to take into consideration while we are going ahead on the desalination pathway, which is to me, it is 100% inevitable. Country like India, which is having something like around more than what do you call roughly close to 20% of the population in the coastal. If one were to consider a kind of a distance of 50 kilometers from the coast, we would be having roughly something like around 250 million of people. And as I said, I mean, the groundwater salinity is on the constant rise. So desalination is going to be a kind of an inevitable, what do you call, solution. And what is another important challenge besides the ecological and environmental challenge? What is the second important challenge is having a kind of an indigenous competency for all the solution in total, of which membrane is one of the most important factor. Where I mean the institute has done significantly in terms of what do you call making indigenous membranes and indigenous module making, which has been licensed. And I'm very happy that one of our licensee is Vikram is there, who is basically, I mean, commercially manufacturing these membranes based on the technology of CSIR. You can hear from him while we are what do you call proceeding on this webinar. And in fact, I mean, the challenge would be in terms of getting a kind of a better improved membranes that can do the processes much more energy efficiently, preferably in a kind of a, what do you call, treating a variety of water, especially a kind of a high saline water, is going to be a kind of a greater challenge that we would be basically facing it. And that would be, I mean, to an extent, it would be covered in the what do you call a presentation of Dr. P.M. Singh. But what is all the more important is, I mean, the necessity has been what do you call very clearly enunciated. The challenges that are basically need to be addressed or very clearly told. How do we do it is something which is the third important aspect, where I think it is important that depending on the requirements at different places or different points of contact, we need to deploy a kind of a multiple technologies. And in fact, I mean, technologies suiting to the kind of what do you call actual locations, whether it is for the domestic use or for the municipal use or for the industry use or for the remote villages use or for the acute shortage spaces use. I mean, we need to use the desalination technologies, especially the membrane-based desalination technologies. Different technologies needs to be deployed. And furthermore, as I said about the energy efficiency, one also needs to have, multiple, what do you call, technologies which are combined to have a kind of an improved energy efficiency. So I think with this kind of an approach, we could possibly attain sustainable desalination. The next, a decade of next decade or two are going to be the very, very critical phase for desalination all over the world. I mean, the fraction, the percentage of people who are using desalinated water is a very, very small fraction, and it is going to continuously going to increase. And as you know, I mean, at least 1/3 of our world's population is having some sort of a water security issues, which is causing a tremendous amount of an impact on the different sectors. So naturally, I mean, one needs to resort technologies, different kinds of technologies, of which desalination also will be one amongst them. So the right choice of technology and making a kind of an probably integrating with the renewable energy for increasing the energy efficiency, and also we firmly believe that a country like India should be going for a decentralized way of desalination approach, where a smaller capacity, mid-sized capacity plants of say something like around 1 MLD to 5 MLD should be distributed across the coast of India for providing the water needs. So if you rightfully, deploy these kind of a decentralized approach with a kind of a rightful management of the reject while protecting the environment in an energy efficient manner, I'm sure that we would be basically quenching the thirst of the people in the decades to come. With this, I once again welcome you all for this webinar, and I'm sure that you will be having at the end of the webinar, you will be getting some sort of clarity how CSIR has been striving hard through its technologies portray in solving the needs of the people. With this, I conclude here, and I would over to you, Shika, for further proceedings.
Thank you very much, sir, for such a nice opening remarks, introducing us about the 80 years, 80 success story of CSIR, about the laboratory, CSM, CRI, and about the technology, the prospects, limitations, responsibilities. So thank you very much, sir. So we'll move to our first speaker to know more about this technology. The first speaker for the webinar is a Senior Principal Scientist from CSIR, CSM, CRI, Dr. P.M. Singh. Dr. Singh obtained his BSc, MSc and PhD in chemistry from University of Pune and started his research career in 1992. He has about 20 years of research experience in development of membranes for different applications. Dr. Singh has held various postdoctoral, research scientist and visiting scientist positions at national and international levels. He has been awarded with the CSIR Raman Research Fellowship and is a life member of Indian Membrane Society and also a life member of Neutron Scattering Society of India. So with this, I invite Dr. P.M. Singh to kindly inform us more about this membrane desalination technology of CSIR, CSM, CRI. Over to you, please. Sir, are we connected? I think there is some issue.
You can hear me, Dr. Shika?
Yes, sir. Yeah. I think Dr. P.M. Singh is not connected. We lost connection.
Hello?
Yeah. Yes, okay. Sir.
Yeah, fine.
Yeah. Please go ahead.
Okay. But let me first share my presentation and
Yes.
then we're very happy. Can you see my slide?
Yes, sir.
Okay.
It's visible.
Okay. Okay. So we're very happy to present this webinar, the membrane desalination technology. Okay. And thank you, Dr. Sika, for nice introduction. And thank you all. Thank you, Director. And thank you, Mr. Vikram. Thank you, Dr. Tina. And all the people attending this webinar. Okay. The water scarcity is a problem, is a global problem rather, and it affects because billions of people and many millions of people die every year because of water scarcity, inadequate supply of water, sanitation and hygiene. United Nations General Assembly Sustainable Development Goal (SDG) goal number 6, point number 6, is to ensure availability and sustainable management of water for all the people. If we look at Indian perspectives, from the information we got from Ministry of Jal Shakti published last year, 25th of March, we have, as Director rightly pointed out, the water now we have in 2021, average annual per capita water availability is 486 cubic meter. You know, this is a huge decline from the water we had when we got independence. In 1947, we had 6,000 cubic meter. So this declining is steep decline. If you see that this is more than a factor of 4. If we decline in this rate, we can expect in 2030, then we can hit something like 1,000 cubic meter only available per capita average annual water for India. And for at this point of time, we will have a real problem. For a country of such a huge population, 1,000 cubic meter is not enough. And water at
You're not audible, sir. Voice is breaking. We are losing contact.
Yeah, looks like.
I don't know if he is informed that we are not able to hear him.
I'm calling.
Yes, sir. He is leaving. He may join again.
Shika, I've sent somebody to, what do you call, he's not lifting the phone also.
That's the problem.
So I think I've told him, to, what do you call, physically go and then tell him to switch over to another network.
Okay. Maybe by that time, if we continue with our talk and we move to
I think, probably, Vikram can, what do you call, go ahead with that.
So let me just first introduce Mr. Vikram to our audience. So we have our collaborator, Mr. Vikram Karunakaram from Uniflux Membranes LLP. Mr. Vikram holds MBA from University of Sheffield and Masterclass in Membrane Technology from Oxford. He has been an entrepreneur since 1997 in the water and wastewater treatment equipment, design, assembly and operation. Amongst the earliest in India to delve into the RO membrane uses for desalination, he has set up thousands of equipment pan-India and abroad through his company Delta Pure Water. And he, along with his partner, set up the first RO membrane casting and coating facility in India at Pune with the technology transfer from CSIR, CSM, CRI. So I invite Mr. Vikram to share his experience in the development of membrane technology with the collaboration of CSM, CRI. So, Mr. Vikram, over to you, please.
Good afternoon, Dr. Shikha. Good afternoon, Dr. Kanan. And good afternoon to Dr. Poyam and Tina ma'am. Hello to you and to the audience. So we have taken the technology from CSM CRI for ultrafiltration hollow fiber, the casting, the spinning machine in 2010, and then subsequently in 2014 we took the technology also for casting and coating of reverse osmosis flat sheet membranes. You would be all surprised, to note that maybe the technology of RO membranes has been developed by an Indian, Dr. Sauri Rajan, in California way back in 1965. So he's credited to be the father of the current sort of reverse osmosis membranes. But if you go back even further, in the 17th century, there was a French scientist who actually showed the power of osmosis through using a pig's bladder, where he treated water and through a pig's bladder and was able to show the process that happens. And even before that, if you go in Hindu mythology, I came across this document which said that the Samudra, the Manthan which happened, actually, if you see in Angkor Wat, the temple, Vishnu is in the center, and then the churning is going on both sides. So there is one side is permeate water, which is Amrut, and then you have the reject water, which is the Vish. So that analogy has been taken, from there. So reverse osmosis is essentially, going back as a technology which has been there for a long time. Technology-wise, I don't want to spend much time on this because most people here would know about what is reverse osmosis. I would like to talk about our experiences, about what we actually achieved in the market and actually made a difference. So by having our membrane technology, especially the UF and the RO, we were able to bring down the price or the cost of RO membranes and ultrafiltration membranes in India drastically. I would say the price even came down more than 50%. Now, because of that, the adoption by customers or users became very high. For instance, if when it comes to recycling of effluent water or sewage water, the clients were very wary about using a technology as expensive as an ultrafiltration, because they would have had to spend more on the capex and more on the opex of running their plants. So they went for simple sand filter carbon filters. Whereas in this case, when we introduced our ultrafiltration membranes at 1/3 of the cost of the regular membranes, which were available in the market, we found a lot of adoption. As a result, many of the plants became compliant. They started recycling and reusing their water for various applications, including for paint shops or for cooling towers. So that became quite prominent. Then when we also put up the RO membrane facility, we were able to bring down the pricing to such an extent that the same sort of concept happened there also. We got a lot of good response from Rajasthan government, Karnataka, Andhra Pradesh, Chhattisgarh and Bihar, because they were setting up these water ATMs in villages, and the water is being sold at about 10 paise a liter in the villages. So that price point has been achieved because of the cost of the membranes being brought down drastically. The running cost also comes down very much, and the availability of membranes in India, no need for importing from all the countries using our dollars, precious dollars. The Delhi government, especially, in the past 2 years, we have been meeting up with them, and we have seeded this idea of 24/7 water supply is one of their commitments. And the way that they're going to achieve it is to recycle and reuse the water from the STPs into open lakes, and those lakes then flow into underground aquifers from where the water is being drawn and passed through reverse osmosis membranes. So Delhi, is always in the news for saying that the amount of water, there's a shortage and there's going to be a scarcity. But the underground water levels in Delhi, I have been told by the Delhi Jal Board, we have about 27 years of water supply about 13,500 cusecs of water underground. And so that is though that might be little saline or highly saline. So depending on the salinity, we will use the type of RO membrane that we have. We have brackish water membranes or tap water membranes can be used for reuse of that water. What I also would like to point out here is that we have supplied some equipment to our Indian Army, the ITBP and BSF. These are mobile, small, backpack sort of carrying UF and RO plants that we made. And these were given to the platoons because these platoons typically are about 15 to 20 soldiers. They go out on a search mission for maybe 4 or 5 days. So they cannot carry so much of water. And so what they did is they used to carry our equipment, and this is with a hand pump. So we improvised a small hand pump with a small diaphragm valve, and the soldiers could dip the water. The inlet water could be any source, any open surface water source, which was contaminated with bacteria, virus, and turbidity. But when it passes through our UF, all those problems are taken care of, and they were able to use this water. So we have supplied a lot to the army. We did actually trials of our equipment at Pokhran in 2012 when we went for the army exercises. So they have the Indira Gandhi Canal coming into Pokhran, and there were expensive RO plants there also installed, which were bringing the TDS of the water from about 125 ppm to below 4 ppm, which is not very desired. So in those places, we showed that we could have an ultrafiltration or a microfiltration plant, which would remove the bacteria, virus, and the turbidity from the water, yet allow the minerals, essential minerals, to remain in the water. So these trials were done, and then the army then started procuring these in a large number. Of course, in the year 2017, we had a opportunity to present our RO membrane to Mr. Ratan Tata, and he was kind enough to grant us time to, and he also signed on our membrane. And then, as ma'am is from Tata Steel, I had the opportunity to meet Mr. Narendran at one of the forums in Delhi, and we did an MOU with for water ATMs. So the Tata water ATMs, which are deployed all over the country, all of them have equipment which is supplied by Delta Pure, which has membranes from Unique Flux. So currently, we are executing a very large order for them in Latihar district for the army. So this was one of the points that we have done. In Jammu and Kashmir, we have done a lot of work. We've been able to do a lot of work in the Jawan Awam Yojana, especially for the army, where the army set up ultrafiltration plants in and around mosques and temples there, where it was given as a free, like a CSR initiative, and people or users there could get good clean water, drinking water at for free of cost. Because in the year 2012 and 13, there was a outbreak of jaundice in Jammu and Kashmir, and some of where the floods were taking place, and because of that, the inferior water quality. These were the challenges which the army tried to mitigate by giving these equipment on their CSR basis. Yesterday only, I have got this inquiry again from the army. This is to develop a straw. This is a straw which is there's a straw in the market called Life Straw, which is a Swiss brand. So the army has sent us a design for the same with some plastic parts, and yesterday only we got this, which is basically a straw which every soldier will carry, and it has a ultrafiltration membrane, hollow fiber membrane inside that, and they will take the water in they have these mugs, and basically you suck the water, and the pressure created by your own lungs will negative pressure will create enough water flow from the contaminated water into good drinking water, which will be safe for the army. So this is one of the other developments we did. For the quick service restaurants, this was one of our good achievements. The FSSAI formulated that any restaurant which has more than 25 people, whenever they have a washroom, toilet, or washing of the equipment, that has to be done through water which complies to IS 10500, which is the drinking water standard. Whereas most of the restaurants are getting water from tankers, which was not compliant and goes into a tank. So there was production of coliform. Often we also found E. coli. So to prevent that, we designed an equipment which was basically UF. It's called a raw water treatment plant, which was UF, the micron filter, UF filter, and then a chlorination. And that in more than 50% of the restaurants in India, the branded restaurants chains, would have this equipment of ours. All this is possible or has been possible because the cost of manufacturing the membranes has been drastically reduced by us. It's a make in India product completely. Currently, as Dr. Kanan mentioned, there is a project that on the 13 coastal states that are there will be a desalination plant installed, and the reject water management will be done in such a manner that the salt, it can actually convert into salt. So, it's going to be technically a zero liquid discharge sort of equipment. So that is what I had to add at this stage. In case there are any questions at any point of time, I'd be happy to answer them. But technically, I have dispensed with talking more on the technical front. It's more on the practical front, which I hope was more interesting.
Yeah, absolutely. On the practical front only. So it was very interesting to know about the army involvement and other states' involvement. Thank you so much for your talk. So till now, we are not yet connected with Dr. Puyam Singh. We'll move to our stakeholders who has joined with us today. Dr. Tina Chakravarti from R&D Tata Steel Limited, Jamshedpur. So before joining Tata Steel, Dr. Tina did her PhD from CSM CRI itself and has held postdoctoral and faculty position at national and international level. So we would like to hear from you, Dr. Tina, about this technology and how it is being applied at Tata Steel in R&D. Yeah, over to you.
Thank you, Dr. Shikha, for your nice introduction. Good afternoon, everyone. Good afternoon, Dr. Kanan, Mr. Vikram, and Dr. Shikha. In last two lectures, we have came across with the introductory session about the membrane and desalination technology. So directly I will go into the project, and I'm going to share my slides. Is my screen visible, ma'am?
Yes.
Okay. So our project title is the Hybrid Membrane Technology for Removal of Chloride. This project actually we are running with the collaboration of CSM CRI. So first let us know the background about this project. As we know that in steel industry, during the steel making process, actually iron ore, it get mixed with the carbon to produce hot metals. Then inside the steel converter, oxygen is purged to convert into the steel with the hot metal. So what is the source of this carbon in the blast furnace? Basically, it is coming from coal, and that is from coke oven. So Tata Steel has one plant that is in Hooghly Met Coke division. It is situated in the Haldia, West Bengal. So our problem is at the Hooghly Met Coke division itself. So there we have the coke oven, and from that coke oven, the coke is purged to the blast furnace at Jamshedpur. So basically this coke, it contains or it absorbs some chloride because due to the due to the process of coke, lot of makeup water is needed. And the requirement of makeup water, which is around 3000 meter cube per day. And directly this water is coming from the Hooghly River. So from the source itself, the water is getting contaminated with chloride. From the source itself, it gets some chloride. And due to the geographical location during the summer, the concentration of chloride, it reaches sometimes 4000 ppm. And this chloride basically it gets trapped by the coke, and when it is purged into the blast furnace, it takes all the chloride all the way to the blast furnace. And due to the presence of high amount of chloride, all pipelines, coke quenching cart and conveyor, everything it's get corroded. So replacement of these pipelines is required almost every year. So this is which consumes a huge amount of cost. So thus we need to remove the chloride from this water. So to solve this problem, actually we have already explored many technologies, but we could not achieve our success like how we need it. Then last year we approached to CSM CRI to avail their technologies or to explore more whether we can achieve our goal to remove the chloride. So our objective was of this project that chloride removal from Hooghly Met Coke division coke quenching water. And the acceptance criteria for project was we need to remove the chloride from coke quenching water at least more than 95%. And as we know that membrane, for every membrane process, mostly in case of RO, the membrane reject generation is the another big issue, because all industries now is looking for zero liquid discharge. And to achieve that, we have to generate very minimum amount of reject so that we can handle it easily by using some other technologies. So that was our second goal, that we have to develop such a technology which can remove the chloride as well as it can generate very limited amount of reject. And this was our project acceptance criteria. Now I am coming to the technologies that we have developed together with CSM CRI. And in last year, we have made one plant that is 1 meter cube per hour in continuous mode. This was the pilot plant developed by CSM CRI. And when we studied with the similar type of synthetic water as well as with the actual water from HMC, we found it gave us satisfaction from the result. And this is the schematic diagram what you can see here for this project that is running now. And now I am coming to the result part. Here you can see that we have treated this technology, membrane technology, with the raw water as well as our synthetic water, and we have achieved more than 97% of salt rejection as well as water recovery. What we achieved, it was 90%. So from the pilot plant, like 1 meter cube per hour continuous mode plant, what we concluded that it will work well for the higher scale plant. So this year we are running another project to take care of one quenching tower, because at HMC we have 8 coke quenching towers. So at this stage we are looking for to establish a demo plant which will have capacity of 20 meter cube per hour, and we are expecting by August 2022 we will have this plant at our HMC Haldia. And from the satisfactory result what we achieved with the 1 meter cube per hour, it is also giving us hope that in future we will be taking care of the whole plant, that is 180 meter cube per hour, with the technology that together we have developed with the CSM CRI. And from the project point of view, I got very much help from the scientists whoever involved in this project, and they are really working very hard for this project. So we are hopeful that in future, maybe within 2 to 3 years, we will be able to solve our problem which we are facing for the coke quenching. Thank you. If you have any question or any discussion, please.
Thank you very much, Dr. Tina, for informing us about the industrial application of this technology as well. So it was very interesting to know. And so we are also joined again with Dr. Poyam Singh. So I would request Dr. Poyam Singh to kindly take over and continue with his talk. Sir, please unmute.
Okay, I'm just sharing again the slide. Can you please see the slide?
Yeah, it's visible.
So where we were earlier,
No, this slide was not displayed that time.
This one, so it is just here.
Yes, sir. The first one only. Yeah.
Okay. Okay. So water scarcity is a problem, and this I have spoken about, and why we require desalination technology to address these issues. So how desalination technology can help? Desalination is the process of removing dissolved salt from saline water. Therefore, it can increase availability of drinking water by converting seawater, which is plenty, and brackish water into this potable drinking water. Conventionally, by thermal evaporation system, we can heat the saline water, seawater. It vaporizes from liquid phase to vapor phase, and again it condenses back to the liquid. So it is a change of phase from liquid to gas and gas to liquid. And it requires a lot of thermal heat. And also you require a lot of electrical energy for pumping this through this system. And again, this is done in the multi-stages and the equipment size is quite big. Therefore, the capital expenditure and operating expenditure is pretty high. On the other hand, we have this membrane desalination system. I've shown here is depicted here. You only pass this seawater through a series of filters. There's no phase change here. We just remove the excess dissolved salt and you get the product water. Here, as shown in the picture, the seawater is pumped from this ocean and goes to the first stage, we say clarifier pre-treatment, where it removes suspended particles, fine particles, and goes to the second stage, membrane system, okay, and where we remove the excess salt and give the product water containing right quantities of required minerals suitable for human consumption. So it's a good product mineral balanced water can be the output from this system. Okay, and the reject stream goes back to the sea. While by doing so, you have only electrical energy input here. Therefore, the energy requirement to do the system running is an order of magnitude lesser than what current desalination requires. And therefore, this RO membrane system is popular and very advanced mode of doing desalination. If you look at the total worldwide installed desalination capacity by technology, you see the 65% comes from the RO only, which is more than twice of what the thermal desalination has installed. Okay, 28% is coming from thermal desalination technology. The rest others is near 7%. So now, therefore, I'm going to spend more on for this webinar on this RO membrane desalination technology, which we have been doing. The first breakthrough of this RO membrane was in 1961-62 by the invention of this Lloyd-Srinivasan cellulose acetate membrane. Okay, by the invention of this membrane, for the first time, this synthetic membrane can demonstrate the production of the drinking water from seawater by passing seawater through this cellulose acetate membrane. And this has done a lot of scientific scientific impact in the modern science, because seawater become now drinkable by this RO process. The CA membrane also made very simply by solution casting. CA cellulose acetate is dissolved in some solvent, and it phase is inverse again to the solid form. So this is the structure of the Lloyd-Srinivasan cellulose acetate membrane. Interestingly, but even though it is of the same material, is asymmetry structure. Have the tight skin structure that acts as a selective membrane layer, which separates salt from water. Okay, and the support structure is highly porous. Essentially, no mass resistance, no resistance of mass flow transport of the permeating water molecules. It only provides the mechanical strength to act as a semi-permeable membrane. So CA membrane are the first generation RO membranes. It allows the water containing low amount of dissolved salt, but it retains water containing high amount of dissolved salt, and this is done under external pressure in excess of the osmotic pressure of the saline feed water. In this way, it is the reverse osmosis process of forcing the drinkable water from seawater through the membrane. I have shown the picture here in bottom corner. In fact, therefore, this is the reverse, again shown depicted here, reverse to the natural process of osmosis, in which the solvent from the dilute stream moves to the concentrated stream solution across the membrane. At CSIR, CSMCRI, this membrane research program was initiated in the year 1969, again with an aim to develop this kind of membrane desalination technology. Okay, this is to meet the water demand, clean water demand through desalination. The institute was successful in developing this kind of CA-based membrane. CA-based membranes, and it was successful to set up desalination plant during 1980 to 1990. CA-based tubular RO desalination plant installed in the of 10,000 liters per day capacity installed in Jodhpur is shown in this picture. Okay, and a similar kind of plant can be fitted inside the bus, and it can now act as a mobile desalination bus, so that it can provide water by going at different places where there is a water scarcity, especially in rural and difficult terrains. This became an interesting subject for the government of India to provide drinking water by desalinating sea water and brackish water. So way back in 1989, government of India gifted 2 such plants to the government of Thailand. Okay? This is a picture of the RO membrane plants given to the officials of Thailand government by then Vice President of India, Mr. K.R. Narayanan. The technology was licensed to BHEL Hyderabad and Aerotech Private Limited Ahmedabad in those days. CA membrane has certain disadvantages, or rather limitations, because CA cellulose acetate is natural polymer. It is kind of food for the bacteria. Bacteria can easily stay, can easily deposit on the membrane surface. While doing so, it clogs the membrane pore. We say fouling in the membrane terminology. It fouled the membrane, damaged the structure, membrane needs to be replaced. Secondly, because it is made from a single step process, okay, phase inversion casting process, we say, it has no much structure, coloring is not possible. Okay? Therefore, the flux and the selectivity has a limited scope of increasing the flux or increasing the selectivity, because the structure is made from a single material and in single step. Third, again, because of natural polymer, it has certain limitations. While the feed water is slightly acidic or alkaline, the CA membrane structure gets degradation, and it cannot perform the way it was used to be performed. Okay, the CA has, even though it was first reverse osmosis, first generation RO membrane, it has these advantages. Now, after that, then to address these issues, 1981, this is a major breakthrough development of invention of this thin film composite membrane that is back in 1981 again. Okay, it is comprised of 3 layers, and this is second generation RO membrane. This is done in 2 stages. Okay, so not many variants, not many coloring of the structure property is possible. Okay, in the first stage, we have the casting of this middle porous sublayer. That can be of different polymer, different blend, and so on. We can color the structure. And this is very important because this impacts on the final coated layer, which is selective active layer separating salt from water. Again, this kind of PFC membrane desalination research initiated in the year 1987 at CSIR, CSMCRI. Now we have a large-scale facility for the production of PFC membrane and also module rolling. Okay, and this was licensed to various Indian membrane manufacturers. Our industry partner, our licensee, will talk about this research product in the commercial domain. So we will hear from him the journey he did from this CSIR, CSMCRI membranes. Just to give you a glimpse of science, of how PFC membrane desalination technology looks like. I'm showing the lab facility we have here. I'm showing here firstly the bottom layer fabric, the image, microscopic picture of that. I colored to distinguish the thread size of the fabric. It's about 20 micrometer. Essentially, there is no flow. There is no resistance to the flow of water. It's easily permeable. Okay. Then we do the coating on top of this fabric. You can see here, this is the white colored material. This is what we coated in a continuous mode. It can be kind of in a matter of 30-40 minutes, we can have 100 square meter length. It's quite rapid coating, casting technique. And you see here, the surface is quite smooth. This is the atomic force microscopy in the nanoscale resolution. You don't see any ups and downs. So it's quite smooth coating. But even then, it is a porous structure. Pore size is 100 times more than the size of the water molecule. So it is almost, again, no resistance to the water flow. But it acts as a substrate layer, uniformly porous layer, so that we can deposit very fine top layer in the nanoscale roughness, okay, nanoscale thickness. It's shown in the right-hand side picture. I've shown here, this is in the nanoscale resolution in the nano domains. It's about 40 to 50 nanometer in the ups and downs the structure. And again, it's a highly cross-linked structure, a three-dimensional structure. There is one typical example chemical structure I've shown here, and also it contains linear fraction, two-dimensional structure. So many things are possible. In the first, as I say, in the first stage, critical point is like the nature of backing layer fabric, composition of the casting solution, overall thickness of the casting membrane, casting speed, contact time between the casting solution and coagulating medium, temperature humidity of the casting chamber, nature of the coagulating bar. It can be many. It can be. So these are the parameters one can do structuring this sub-layer, and that sub-layer can help in making different types of membrane structure in the second stage. Okay, in the again second stage, we have different parameters to optimize. Okay, and while by doing so, we can have many variants of the membrane, the PFC membrane types that can cater for different requirements of the desalination plant. When these membranes are made, again, this can be fitted inside the bus or van, and it can go places. I mean, especially at the time of natural calamities. You know, natural calamities, the first thing, the immediate outcome of natural calamity is water is getting contaminated. There's no drinking water available. So this kind of mobile RO unit is very helpful providing drinking water. Any water, source water, can be converted to the drinking water, because this van is fitted with the membrane module. You pass the dirty water through this module and you get pure water. And again, this filtration can run on hybrid energy system. For example, if there is no electricity over there, then it can run through the vehicle engine, or also it has solar panel, and energy also can be taken from the solar panel. This unit, this mobile desalination, goes every coastal states of India where there are natural calamities. For example, in Odisha, Tamil Nadu, Uttarakhand, Gujarat, West Bengal, and Maharashtra. Just finish little bit, just show you the glimpse of the deployment of this desalination technology. It is a full proven technology, and I have not shown because not enough space to talk about solar desalination, defluoridation, come desalination. Okay, and so I've just shown here the specialty we have is to customize the plant to suitably cater to. For example, if you have the water is contaminated with fluoride as well, in addition to the salt, we do the defluoridation and the desalination. Okay, so this is just the snapshot of the few seawater and high brackish water desalination plants we deployed over the years. Okay. Still, for sustainable desalination, we still require a better membrane separation technology, which is worldwide work is going on to that will allow the usage of less material, low energy consumption. It should permit recovery, reuse of process stream. So kind of two-dimensional objects as a filter like graphene oxide. These are the futuristic membrane in terms of advanced membrane development. That we have been working along the way. Okay, and so I conclude here and thank you, and over to you, Dr. Sika.
Thank you very much, sir, for describing us about this technology that has been developed at CSM CRI. So we have already heard from Mr. Vikram about the application at various fronts of this technology, and also we heard from Dr. Tina about the industrial application. So it was really very interesting and very nice to know about the technology for desalination of water and of saline and impure water, and which has been originated from our own lab, CSM CRI. So as Director Sir told, in a country like ours, which has most of its land surrounded by coastal line, technologies like this is of great importance and used to meet the demand of clean water. So now we keep this forum open for discussion, and I shall be taking few questions from audience. I'll just have a look. So yeah, our first question is from Mr. Kunal Roy. He asked, what is your RO membrane rejection rate at 200 ppm TDS? RO membrane rejection rate at 200 ppm TDS.
I think question 3, there is something wrong. I mean, the questions is not right, correct. 200 ppm is, in fact, it is nothing can be done because it's already good water. 200 ppm. There's a mineral, the mineral water. RO, you have mineral water is having around 225 or 250 ppm. Okay, so I don't know.
It should be 2000 ppm.
2000 it should be, yeah.
Maybe if it is 2000, yeah.
Okay. So maybe we'll move to the next question from him only. Is there any membrane technology available to reduce TDS and remove contamination without wastage of water?
Yeah, actually, you see, so much fun. Yeah, we can reduce it. We can customize. We can tailor. We have different membrane types. For example, we can also bring down the seawater to the drinkable kind of range, or if it is like 2000 ppm, we can only reject 90% or less, so that you keep like 100 ppm or more in the product water. This all is possible. We have to select, we have to make the right choice of the membrane, and then we do the desalination.
I'd like to add here that it's not just this choice of the UF and the RO. There are other technologies like EDI which can be used, or seawater desalination membranes post the brackish water. We have achieved zero liquid discharge systems also, where we have given back just power. So there is no water discharge from the factory, and this is an automobile company in Indore, large automobile company, where we have combined their effluent water and their sewage water, and then treated them through a series of UF and RO, EDI, and given water back at every stage through an MVR, which is the membrane vapor recompression at the end, and you get powder. So no water wastage.
Nice. So yeah, we have few more questions. There is a technology for hollow fiber membrane and this TFC RO membrane. So what is the difference between these two membrane technologies?
Mr. Vikram, would you like to answer that?
Yeah, so hollow fiber is an ultrafiltration or a micron filtration membrane technology that we have. That is not for removal of TDS, it is for removal of turbidity, bacteria, and virus. The pore size of the membrane would be 0.01 micron, whereas the flat sheet RO, reverse osmosis membrane, has a pore size of 0.0001 micron. So there the TDS dissolved impurities will also be selectively removed. So both are different technologies. There is a hollow fiber RO membrane technology also that only one company in the company in the world, Toyobo, has in Japan. It's not available here.
So this RO membrane can also be used to remove pathogens or other toxic metals present in this contaminated water. Can this be used?
Yes, because RO is the finest. I mean, you are removing the smallest ions and the it's a molecular level CV, and the bacteria and pathogens and the very big particles. It's a big size, like in the 0.1 to micrometer. So obviously, all these can be removed. When RO is the salt, it is guaranteed that the other contaminants also will be removed.
Okay. So we have another question, Mr. Mahesh Pujara. He wants to know what is the uses of reject water of desalination of RO plant. Yeah, Mr. Vikram, any comment on this?
So reject water, ma'am. Mr. Modi also said once that a glass is half full and half filled with water and half filled with air. So the glass is always full. So you have to look at, in totality. So seawater is not usable at 40,000 ppm. You cannot use it for drinking. But by using an RO membrane, at least you can make some percentage of that which is usable for drinking for humans. So similarly, reject water, of course. Now CSM CRI, I think, is developing that technology where the salt, there will be some salt recoveries and all, but that is a technology which I think Dr. Kanan would be better off.
I will appraise Shikha. Yes, I mean, I think as I said in the beginning, I mean, reject management is something which is very, very critical. It also depends on what is the kind of a feed water. Depending on that, I mean, different kinds of a solution can be used. One is, as Vikram is telling, I mean, which I've also mentioned in the opening remarks, that one can make a kind of a salt out of it. Okay, you can, if subject to availability of the land, one can crystallize salt out of it. Okay, the second option is, I mean, if the salinity is not that great, one can create a kind of a halophyte parks, and these halophytes are salt loving and salt uptaking plants, which can which can use the saline water as a kind of a source water for its growth. And these halophytes are also useful for making different kinds of high value materials. That way also one can basically look at it. And these are some of the advantageous avenues one can basically think of, and to make it as a kind of a ZLD management. If all these things are not possible in the given scenario, most of the countries in the world, they are usually doing a kind of a discharge in a kind of an ecologically safer manner back into the oceans.
Okay. Yeah, so we'll move to another question from Udaya Bhanu. What is its efficiency in removal of sulfates, carbonates, nitrates, and chlorides? So chlorides we already saw from Dr. Tina's talk. So, yeah. Dr.
Yeah, please. Yeah, these all the sulfate, these are all bigger ions. I mean, only chloride is rejected, sulfate obviously will be rejected even better. Okay, I mean, again, as Director Dr. Kanan said, again, it depends on what kind of the feed water characteristics. I mean, the amount is also important, and also counter ion presence is also important. So we have to look at those things. Otherwise, even if it is in thumbs rule is that all bigger ions, when chloride is rejecting, will be rejecting more than what chloride is rejecting.
Okay, so thank you very much for your responses. I think we don't have any more questions. We'll conclude our session here. So thank you everyone once again. It was really great listening to all of you and was interesting to know about this membrane desalination technology developed by CSIR CSM CRI. So I now request Director CSM CRI, Dr. Kanan Srinivasan, once again to kindly deliver the closing remarks for the session, please.
Yeah, thanks, Shikha. I think it was again a fantastic, webinar. Certainly, I mean, as I said in the beginning, desalination is not an option, it's a necessity. Okay, it is going to be a necessity not only for the domestic sector, but also for the industry sector. What Dr. Tina said is one such an example. Okay, I mean, there are many industries which are having a kind of a saline water which needs to be treated, okay, or a kind of a what do you call water which is having a kind of a certain ions that needs to be treated. So and desalination, we call the process desalination. Any removal, the technology, the membrane technology that has been developed can be suited to variety of what do you call applications. The membranes that were designed for the desalination were the same membranes were basically treating the med coke water. Okay, nobody would have thought. I mean, this membrane, these kind of a membranes would be basically put into repurposed for these kind of an application. And something very similar, what Vikram was telling. I mean, there is another technology which is called as electrodialysis technology, which is amazing technology in terms of what do you call water, what do you call rejection, as well as water, what do you call the amount of water that you can basically take out. Okay, from the what do you call feed water. Okay, the recovery, we call it as water recovery, and water recovery is pretty good in electrodialysis also. It has its own limitations, like it cannot treat a kind of a very high saline water, but in a kind of a normal saline conditions, a brackish, let's say something like around 3000 ppm TDS, I mean, it can treat with a kind of a very high recovery with a high what do you call salt rejection. So adoption of the technologies, multiple technologies, is very, very important. And these days, the technologies that are going to be seen in the future, and this is the direction that the entire world is going, in terms of energy efficiency, as I said in the beginning, there will be a lot of a kind of a connected technologies will be in place. It's like, for example, combining reverse osmosis with membrane distillation. It is combining ED with electrodialysis with reverse osmosis, and these kind of an hyphenated technology, or like what he was telling for one of the places, where combining a kind of a multiple vapor compression technology, MVC technology, with what do you call the reverse osmosis. So there will be a kind of an hyphenated technologies will be basically put into place with extraordinary amount of energy efficiency and recovery traits, and these are going to be the kind of a future. And for all these things to happen, right design of the membranes and right design of the membrane configurations are going to be very, very critical. And that is where, I mean, the institutions like us will be playing a kind of a greater role. And this is what, I mean, besides this, as I said, it requires a kind of a paraphernalia of other, what do you call, components needed for a desalination plant. Also needs to have a kind of a what do you call indigenous competency base. I mean, it's not like, I mean, I create only one what do you call artificial heart. With that, I mean, the whole body will run. No, it cannot. So you have to have multiple things also. So there is a huge amount of a drive that is happening in terms of what do you call multiple components indigenous manufacturing is also happening in the country. And most importantly, what will you do with the used membranes? What will you do with the used membranes? Once, like, it's nobody thought in 1990s, okay, when the mobile phones were about to be born, okay, or just born, okay, nobody thought lithium recovery from the used batteries is going to be a problem. And in 2020s, less than 30 years, we are now finding a kind of a lots and lots of investment in R&D by multiple countries are engaged in the recovery. The waste recovery is going to be one of the greatest challenge. Something very similar, membrane based. At this point, I've mentioned in many of the forums also, M waste. Now we call it as E waste, and something very similar, M waste, is likely to happen in the future. And we need to have a kind of a technologies to address that also. So there are some R&D efforts are taken at this institute, which is going to have some sort of an implications in the years to come. So I mean, the challenges are many, necessity is very much there, and we need to have a kind of a joint forces with the concerned stakeholders for this to happen. And that's the way that we will be basically catering to the large section of the population of this country. So with this, I once again, I mean, thank the CSIR, especially the SCDD team, for what you call choosing this membrane-based desalination technology as one of the flagship technologies of CSIR to show to the entire world. Thank you very much, Shikha.
Thank you very much, sir, for the closing remarks and summarizing the session. So this is for all the viewers. There will be a blog on this technology on the CSIR website. You can see the blog online and you can have more information on this. So join with us tomorrow to know more about another success story of development of biojet fuel from another CSIR lab, Indian Institute of Petroleum, Dehradun. And stay tuned for the upcoming sessions of CSIR success story. So bidding you all goodbye for now. Stay safe and have a nice day.